In our EGR 598 class, we were tasked with researching and designing a bio-inspired laminate robot. Laminate robotics offer a unique platform for rapid manufacturing of foldable designs, which allows for frequent design iterations.
The biological inspiration for our robot is the tortoise, which is best described by a static robot with 4 legs that move independently to grant 2-dimensional motion. The tortoise only moves 1 leg at a time. The incremental pattern of the leg movement is important for stability as 3 legs are always on the ground, which is a characteristic of a static robot.
Using a tortoise-inspired static foldable laminate robot as a test bed, we can measure the weight distribution of the robot over its 4 legs using a flex sensor. This works in conjunction with materials with known properties cut into different shapes to determine the optimum foot that bends at a constant radius. The 4 sensors will help investigate how to improve dynamic weight distribution for moving over uneven surfaces.
Over the iterations, the methods used to transfer motion from the servos to the legs evolved to improve strength and efficiency. From iterations 3 to 4, the 2-legged mechanism was mirrored to create a 4-legged mechanism to meet our project requirements. Also, the pushrod extension was made perpendicular to the device to offer a greater range of motion, and the material was swapped for a thicker cardboard.
From iterations 5 to 7, an important improvement made was the method of motion transfer from the servo to the upper leg. The upright extension that attached to a pushrod was intended to be rigid, but ended up either bending or breaking. This was fixed by creating a pull tab that moved with the leg rather than against it, and actuating that tab with a custom servo horn. Some necessary hardware for the design, such as the servo horns and mounts, weren't available as off-the-shelf parts, so they had to be designed in CAD and 3D printed. The laminate manufacturing process requires that the hinges and holes of the device be cut first. This includes the paper, adhesive, and flexible layers. In our case, we used castellated hinges because they are stronger than flat hinges. The paper layers must be glued by the adhesive layers to the flexible layer using a heat press, and then after that, a second pass by the laser cutter removes the laminate from its outline and frees any moving links.
Sensing was accomplished by using a flex sensor, which is a variable resistance sensor that changes resistance with respect to its radius of bending. In order to optimize the sensor, the foot is made out of a material with known properties to measure its deflection. Using the cantilever beam model for deflection, a changing width with respect to length can be found to ensure the sensor bends with a constant radius, increasing sensor data accuracy.
The Adafruit Pearl Trinket microcontroller was used to drive all of the actuators. Motion of the robot was achieved through the use of inverse kinematics to determine the position of the foot in relation to the body. Each foot is programmed to move while the others are on the ground, so only one foot is allowed to be raised at a time.
Ideally, we would have liked to figure out the best shape of foot by looking at the best data output by the deflection sensor, and also use that data to better balance the device. However, because the data that the legs we tested was always difficult to interpret, we were unable to come to an accurate conclusion. Based on our calculations, we do think that a rounded arrowhead shape is optimal for performance.
In looking at the future of this project, the most important improvement to be made would be to choose a more rigid material for the rigid layer of the laminate, or design the limbs to withstand more force without buckling. There is also the possibility of changing to a better microcontroller to avoid glitching. With better stability, we would be able to record usable data and come to legitimate conclusions about our device from there.